Use implicit differentiation. Well, before we learn how to use implicit differentiation, we should probably talk about what implicit differentiation is. So, what is implicit differentiation? Well, implicit differentiation is just the differentiation of an implicit function. Oh, duh, easy, right, no problem. Except what is an implicit function? That was a great question. So, next up, we need to dive in and talk about what is an implicit versus what is an explicit function. Fortunately for us, we've been working with explicit functions for most of our mathematical journey, because an explicit function is just a function where the dependent variable is isolated on one side of an equation. So for example, an explicit function we've been working with is y is equal to x squared plus x minus 2. This is an example of an explicit function. We have the dependent variable y isolated on one side of the equation. And we know that our dependent variable is y, and y represents the output, and our independent variable is x, and x represents the input. And again, this is just normal, basic function material. But now we're given these basic functions a name, and these functions are explicit functions. Alright, so great. But going back to our original question, what is an implicit function? Well, an implicit function is just a function where the dependent variable is not isolated on one side of the equation. That means that we are dealing with functions where you can't get the y value by itself. And an example of an implicit function would be something like x squared plus y squared equals 1. Our standard circle function. Now, even though a function is implicit, meaning we can't get the y value to be by itself, that doesn't change our independent or our dependent variables. Our dependent is still the output, which is y. Our independent variable is still the x, which is the input. So nothing changes. It's just the way that we can write the function. So let's take a look at some examples. What are some ways that we can write a function explicitly versus how we can write something implicitly? So here we go, two columns, explicit and implicit. Well, let's start out with the explicit function, y equals 5 minus 3x. This is explicit because the y is isolated by itself. However, we could write this in implicit form, or we could write this as an implicit function by doing 3x plus y equals 5. And if you remember way back when we first started learning about linear equations, this is the standard form of a linear equation, which remember was ax plus by equals c. And that is the implicit form of our linear function. All right, let's take a look at another example. So another implicit function is y equals 1 over x. We can also write this implicitly by multiplying both sides by x and getting x times y equals 1. Again, another implicit function. And as you can see, we should be able to write any explicit function as an implicit function. However, the problems start to come out when we try to write an implicit function as explicit. And we're not always able to write implicit functions as explicit. And the most common, most famous implicit function would have to be the one we previously mentioned, x squared plus y squared equals 1. Because in order for us to get the y value by itself, we would have to subtract x squared from both sides. And that would leave us with y squared is equal to 1 minus x squared. We could then take the square root of both sides to get y is equal to the square root of 1 minus x squared. And you're thinking, what are we talking about? We just did it. We just wrote it explicitly. However, Remember, whenever we take the square root of a variable, there's always the possibility of the plus or the minus piece, which means we cannot write this explicitly because we'd have to break it up into two separate pieces in order to look at it. Therefore, two separate functions. So this is an example of where we cannot write an implicit function in explicit form. Which means if we want to take the derivative of an implicit function, we need to talk about a new technique, which you probably guessed is known as implicit differentiation. So here we go. Let's talk about implicit differentiation, or what makes implicit differentiation so difficult. Because really, it shouldn't be that difficult to take the derivative of x squared plus y squared equals 1. However, the difficulty comes into knowing when and how to use the chain rule. So implicit differentiation is all about the chain rule. And let's talk about why that is. So let's take a look at an example. We'll take a look at x squared plus y squared equals 7. And we are eventually going to take the derivative of this. But before we can take the derivative, let's just pull this apart, do some basic review here. So as we said, the x value represents our input, which we also know is our variable. And even though this is an implicit form, the y still represents our output. And we know that our output can also be called a function. So in this particular problem, x is our variable and y is our function, which means we're going to have to take the derivative of these things a little bit differently. So I'm just going to do some side work over here, and I'm going to take our x squared, and I'm going to take the derivative of it. So we'll have d dx of x squared. And we know that we can use the power rule to take the derivative of x squared. That's just going to give us 2x. And good, we're done, because remember, x is just a variable. Now let's take a look at the derivative of y squared. So d over dx of y squared. And now here's where it gets a little bit different, because we are taking the derivative with respect to x, because x is our variable. But we don't have an x in the expression. It's a y squared. And remember, y represents a function. So if we think about this, we can see that the inside of our function here is going to be y, whereas the outside of our composite function is going to be the inside squared. So we can use the chain rule and the power rule here. So chain rule says take the derivative of the outside function first, which means we will move the 2 to the front, and we will subtract 1 from the exponent. We'll then put the inside, which is y, back in, but then chain rule says we need to multiply by the derivative of the inside, which is going to be dy over dx. And unfortunately, we can't take the derivative of y because we don't know what the actual function is. So therefore, this dy over dx has to stay there. And we'll talk a little bit about this more as we continue solving these problems. But we can rewrite this then as being 2y times dy over dx. And again, we need this dy over dx because it represents the chain rule. It is the derivative of the inside function. All right, so now let's combine these two pieces together, and let's first take, try this again. Now we can combine these two things together and use implicit differentiation to differentiate this function. So as we said, the derivative of x squared, that's just a variable, so that'll be 2x, plus, and then we said the derivative of y squared is going to be 2y times dy over dx. And then we need to take the derivative of 7, and the derivative of 7 is going to be 0, because 7's a constant. All right, so great. We have 2x plus 2y dy dx equals 0. What do we do from there? Well, remember, we're trying to find the derivative. And in a way, we've already found the derivative, dy over dx. That represents the derivative. So now that we have that piece, we just need to get it by itself to figure out what the derivative is. So we can come in here and I'll subtract 2x from both sides to start to get that by itself. So let's see, we're going to be left with 2y dy over dx is equal to negative 2x. And again, we're trying to get the dy dx by itself because that's what the derivative is. So we can divide both sides by 2y, and that's going to give us dy over dx is equal to negative 2x over 2y, which we can simplify down to be negative x over y. So therefore, the derivative of x squared plus y squared equals 7 is just going to be negative x over y. And boom, there we have it. Implicit differentiation. All right, so now that we've kind of looked at the basic idea of how to differentiate an implicit function, let's quickly go over the how to use implicit differentiation. And there are general guidelines for implicit differentiation. So step 1, like we did in the previous example, is we want to differentiate both sides with respect to x. Then step 2 is we want to apply the chain rule whenever we're differentiating y. So that essentially means whenever we take the derivative of y value, we're always going to multiply the derivative expression by dy over dx because we need the chain rule. And then finally, we want to get the dy over dx by itself because the dy over dx is our derivative, so we need to isolate it. And to get the dy dx by itself, you can follow the subsets, which state get all the dy over dx terms on one side, factor out the dy dx, and then solve for the dy dx, aka get it by itself. So let's go ahead and let's take a look at an example. So our first, or I guess technically our second example, is going to be find dy over dx of 3y cubed plus x squared equals 5. All right, so now we can differentiate this, no problemo. All right, so we can come in here, we want to differentiate the 3y cubed first. So we'll use the power rule here. We'll take the 3 in the exponent, multiply it by the 3 as the coefficient, and subtract 1, giving us 9y squared. But remember, we just took the derivative of a y, so that means we need to multiply it by dy over dx. Thank you, chain rule. Then plus, we're taking the derivative of x squared, which is going to be 2x, because remember, x represents the variable. And that's going to equal, well, what's the derivative of 5? Derivative of 5? That's 0, so boom, 0. And there we have it. We have taken the derivative. Now all that's left is the algebra. So we want to get the dy dx by itself, so I can come in here and I can subtract 2x from both sides, boom, 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 boom. And that's going to leave us with 9y squared dy over dx is equal to negative 2x. And since we want to get the dy dx by itself, we can then divide both sides by 9y squared. Zoop, gone. And it's going to leave us with dy over dx, or the derivative, being equal to negative 2x over 9y squared. Boom, boom, boom. Done. Differentiated. So with these particular problems, there's nothing really too tricky or difficult about it. Just the mistake students often make is forgetting whenever we take the derivative of a y expression, we need to multiply the derivative by the dy dx. Chain rule. All right, so let's take a look at another example. So next up, we want to find dy dx of y to the fourth minus 2y is equal to 4x cubed plus x. All right, so let's just dive right in. Let's start taking some derivatives. So the derivative of y to the fourth is going to be 4y cubed. But don't forget, We just took the derivative of a y, therefore we need to multiply it by the chain rule, dy dx. Then minus. The derivative of 2y is going to be 2. And since we took the derivative of an expression with a y in it, we need to multiply by dy over dx. This is another common mistake, because students look at this and like, the 2 doesn't have a y, so therefore I don't need to add the dy dx. Again, that's a trap, because the original expression we took the derivative of does have a y, which means we need the chain rule. However, we don't need to worry about any of that when we take the derivative over these x values, so we're going to have 12x squared plus 1. Alright, so let's see, we took the derivative of both sides. Next thing we do is we need to get the dx over dy by itself. And I can see that both terms on the left-hand side have a dy over dx in them, which means they have something in common, which means we can factor that out to leave us with dy over dx times the quantity 4y cubed minus 2. And that's going to equal 12x squared plus 1. Great! We turned 2 dy over dx's into 1, so now we just need to get that 1 dy dx by itself. So that means I can come in here and I can divide by the 4y cubed minus 2, and I can do that to both sides. Shoop, cancels out, leaving us with dy over dx is going to be equal to 12x squared plus 1 over 4y cubed minus 4. Boom, 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 boom. Done. Derivatized. Yep, mid upward there. Gotta love them. Alright, let's take a look at another one. So next up, we want to find the derivative of negative y to the fifth plus y minus 2 is equal to negative 2x squared plus 1. Alright, so let's go ahead and start taking the derivative. So here we're going to have negative 5y to the fourth. And since we took the derivative of a y, we need the dy over dx. Plus, well, the derivative of y we know is 1. And since the original expression had a y, we need the dy over dx because of the chain rule. And I just put a plus, and that should be a minus, so let's fix that. Minus, well, the derivative of 2 is 0. Boom, done. And that's going to equal, let's see, derivative of negative 2x squared is going to be negative 4x. Derivative of x is going to be 1. And since we're taking the derivative of our variable x, we don't have to worry about the chain rule. There is no inner function. Alright, so I'm going to simplify this down a little bit to give us negative 5y to the fourth dy over dx plus 1 dy over dx. And that's going to be equal to negative 4x plus 1. And just like the previous problem, both of the terms on the left-hand side have a dy dx, which means they have a common factor, which means we can factor that out, giving us dy over dx times the quantity negative 5y to the fourth plus 1, and that's going to equal negative 4x plus 1. And then our last step is to get that dy over dx by itself, so that means I can divide both sides by negative 5y to the fourth plus 1. Boop, gone. As I've said before, and I will say again, math is always more fun with sound effects. So let's see, we're going to have negative 4x plus 1 over negative 5y to the fourth plus 1. And now students here are like, wait a second, I have a negative in the top, negative in the bottom, so those can cancel out, right? Don't fall into that trap. Remember, in order for us to cancel things out in the numerator and denominator, they have to be a factor of the numerator and denominator. They can't just belong to one individual term. So this is our answer. If you wanted to cancel out that negative number, you could. You would then just need to factor negative 1 out of the numerator to give you negative 1 times the quantity 4x minus 1 over, and then factor negative 1 out of the denominator to get negative 1 times the quantity 5y to the fourth minus 1. And then we can see they both have a common factor which can cancel out, leaving us with an equivalent answer of 4x minus 1 over 5y to the fourth minus 1. And again, Since that is an equivalent answer, that is also the derivative here. And either one of those answers is correct, and Newton should accept both of them. All right, folks, and that is it. That is using implicit differentiation.